So we're going to start recording a second time because we had a little snafu earlier. So mass spec, what is the point of mass spec? Mass spec, really what I want you to get out of this is not the nitty-gritty details. Don't stress on that. Just realize that what we're trying to cover is the bare essentials behind what the technique does and how it roughly works. So mass spec is kind of a CSI investigation, if you will. You're looking at the analysis of the exploded parts. So a lot of some CSI investigators, bomb experts, will go through and look at the aftermath of an explosion and be able to piece together where the bomb was located, how it was assembled, who made it even, because of the characteristic pieces. And so they're able to reassemble it. That's what a mass spectrometer does. Or the person that analyzes it, that's what they do, right? So except in the case of the mass spectrometer, we're not analyzing just a single explosion. We're analyzing probably upwards of millions and billions of explosions because we're looking at molecules. We put a small amount of our sample in, remember how tiny moles are, a small amount of our sample in, and then the mass spectrometer explodes all of those molecules. Those molecules will all break apart into varying pieces. The pieces that break apart are going to be more stable. We wouldn't expect a piece to kind of break off that would be unstable because it just wouldn't form. It would react immediately with the pieces around it. So it explodes apart into a variety of these pieces. We now need to separate those pieces away from each other so that we can interpret what those pieces are. And so that's the rest of the instrument. You get a nice long tube, you get a carrying gas that helps kind of push each of those particles through. The smaller, lighter pieces will move much faster because they're smaller and lighter. The heavier pieces will take a little bit longer. Okay? The other part that shows up in your mass spectrometer is this magnet. When we're looking at those pieces that explode apart, they're typically charged. And so what the magnet will go through and do is to help sort out weird charged species so that the particles that end up making it to the detector have a very particular charge, and in this case, a +1. Okay? So what this is going to do is give us an output that relates the mass of the particle to the charge. But since the charge is always +1, our particles are coming out as just their mass. So that distance traveled helps to kind of sort those out. And now our detector just kind of says, well, what hits me? Okay? And it correlates that time to a particular mass. And that's about it. So if we were running along and running it, we might see nothing hit the detector. And then at 20, we see 20 particles hit. Well, okay, now it says, well, 20 things hit me. Okay, and now 21, well, nothing's hitting me. And so we get a flat line again. And now at 32, okay, I get 400 particles hit me. Okay, we'll note that that height difference has to do, or the amount of particles hitting has to do with the stability of that piece. So 400 particles means that 32 mass was much more stable than that, I think I said 20 mass. Okay? And we can use that to help kind of piece together what our starting material was. And that's kind of neat. Okay? And so, yeah, that's mass spectroscopy in roughly, a little nutshell. Okay. So with that, we'll go ahead and dig into this a little bit deeper. If we look at an actual molecule, our sample is going to have, like I said, millions of these. Okay, tons and tons and tons of these. So what happens is our electrons come in, our electron beam in one form of mass spectroscopy comes in and it ejects an electron from the molecule. Okay? And you'll note that we're saying 3 results here. Okay? Well, in this case, what we're saying is not that that one molecule turns into those 3 things, but that there's 3 of these molecules and there's 3 possibilities for how that electron could have ejected or broken the molecule. Okay? And so that's what they're trying to show here. So in this top case, what happened is that electron came into that bond and it kicked 1 electron out. Gone. So the net result is that our particle is now positive because it's lost an electron. right? And, yeah, it's lost an electron, so it's now positive. But we haven't really broken the structure apart. We just ejected an electron that didn't actually destroy the molecule. So what this is looking at is now the molecular weight of our starting compound. So this is typically known as the M+, right, or I believe our parent peak. Okay? That value, when we see that come through, will now be the mass of our starting compound. That's kind of useful because we could now get a mass of what our starting compound was if we didn't know what it was. The other possibility is that that electron comes in, kicks it, but this time it destroys the bond. Note, the bond is now broken. Okay? I don't have that bond anymore. Well, the instrument only detects positively charged particles. So this hydrogen radical, I don't see. But what does make it through is the rest of this. Okay? And so now I'm going to see a signal for that. Well, that is now one less than the M+. Why is it one less? Well, we got rid of a hydrogen, and the mass of hydrogen is 1. So there we go. That would just be one mass less. And so we would now see a signal for that as well. We don't have an extra name for that other than maybe other pieces. Last possible option that we're looking at here is the electron comes in again and it breaks, but this time it breaks out of the middle there. So now we don't have a connection between those two carbons, and we're going to get that radical again and a cation. This piece is again not seen because it's not charged. It has to have that positive charge, and then this piece is what carries through and hits our detector. So we end up now with 3 potential things showing up. So if we looked at our mass spec, we'd see our MZ, mass to charge, okay? And then we'd see signals. Our signal 1 would show up furthest to the right because it's the largest mass. Our signal 2, which I should have color-coded here, blue, should show up really, really close to it because it's very close in mass. And then our signal 3 should show up significantly lower, roughly halfway, because it's about half the mass. Well, what's the height of those individual signals? In this case, I haven't addressed the height. That height has to do with the stability of each of those pieces. The more stable the piece is, the more likely that that action happened, and we would therefore see a larger signal come out of it. Okay? So that stability now has to get addressed with looking at what makes each of these reactive. That thing that makes it reactive is that positive charge. So we need to know something about how positive charges are stable or unstable, because they don't form as often, in our instrument. Okay? And if we know something about that stability, we can then predict how a molecule might break apart, and also therefore reverse engineer, now that I have this piece, how could that have formed from the starting structure, okay? An unknown starting structure. So the first thing we have to do is understand something about cation and radical stability, okay? So the first thing I want to kind of point out here, and then we're going to get rid of it, is that we are looking at radicals in mass spec. Cations and radicals are forming. The radicals we largely ignore because they don't make it to the detector. So why am I including radicals in this discussion? Right? Well, the important thing to address here would be coming back to what makes each of these structures unstable. Right? And if we were to go through and evaluate each of these Lewis structures, we would say that they were all bad Lewis structures. Right? And we would say they're bad Lewis structures because they're missing an octet. Okay? That missing octet is common for both cations and radicals. They're both missing an octet. And it turns out because they're missing that octet, even though the radical has that extra electron, its chemistry is most closely similar to that of a carbocation, okay, or the positively charged species. Which means when we think about radicals and their reactivities, they mimic carbocations. Okay? Now that we've done that, I'm going to get rid of the radical, and I'll actually want to look at the radical. And I want to now think a little bit about the cations. So first thing I want to think about when we're looking at our cations is what would the hybridization be of the carbon in each of those cases? 3 electron groups, our hybridization is sp2. And if we were to go through and use our knowledge from Unit 1, each of those points is an sp2. Well, what's describing that cation? Well, that positive charge is now an empty place where there's no electrons. There's an empty p orbital. That p orbital is above and below the plane, and because we're showing these as sp2 trigonal planar, the plane of the paper or the screen, that p orbital is coming at you and away from you. Right? So another way that we could consider this is if we turned it on its side, where we have a hydrogen now coming at you and a hydrogen going away, that p orbital we could draw now in the plane of the paper this way. So we're turning the molecule so that we can see that a little bit better. Okay? So that hybridization, not super critical to our argument here, but we need to be familiar with that shape, because when we talk about cations, you need to be familiar with the shape so you can predict its reactivity. What does that mean? I can place electrons in the top or the bottom of that shape because the electron or the empty orbital is both equally above and below. That's an important observation that will come back and haunt you if you don't remember it now. We'll also talk about it then. So back to our cation. What makes the structure unstable? We already addressed that. It's missing an octet. Okay? So if it's missing an octet, it needs more electrons. Okay? If I'm missing electrons, what's going to describe it being more or less stable? Okay? Well, if I was missing more electrons, I would be more unstable. If I was missing less electrons, I would be less unstable. So we could go through and evaluate these and look at the electrons in each structure. And around that first carbon, we've got 6. The second one has 6. The third has 6. The fourth has 6. You go, well, they all have the same number of electrons, Mike, so your argument is invalid. They have the same number of electrons in the bonds immediately next to the carbon. But just like when we did R and S, okay, we first look close, and then we stepwise look further and further out. And when we look at all 3 of these, we'll notice that yes, they may have all the same 3 bonds, but does that mean they're all identical? Well, if we start at the top, hydrogen, 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 and we move to the next one, well, hydrogen, hydrogen, there's a difference. Now we're bringing in carbon. And as we progressively go through, you'll note that we are switching between hydrogens and carbons. Okay? And now the question becomes, well, does that matter? Well, can you tell a difference between hydrogen and carbon? Yeah, we can. One's an H and one's a C. That's a bit snarky, so let's take it a step back. Is there another difference? Why do we use a different symbol for C than we use for H? And of primary importance to consider are electrons. Carbon has more electrons than hydrogen. Right? So if we were to go through and take a look at that very first structure, the top one, okay, we had the 6 electrons in the bonds. Hydrogen doesn't bring in any more electrons. They're already accounted for in the bonds. So I would make the argument that there are 0 extra electrons around that carbon, that center carbon. When we move to the next one down, well, the hydrogens aren't contributing any extra, but that blue carbon has more electrons. Okay? And depending on how you want to count that, you could come to different numbers. Carbon officially has 6 valence electrons, so let's go ahead and say 6, 6 total electrons, but 1 was already in that bond, so it's really only contributing 5 electrons. Okay. Well, does that allow us to see a difference here? Well, yeah, that would suggest the top one has less electrons around it, okay? Whoops. And that's going to change its stability. which means we really need to take a look back here. Okay? Did I actually write that out right? If we're missing electrons, more electrons means more stable, not unstable. Okay? Why? What made it unstable? It was missing electrons. If I give it more electrons, that fixes the problem. It makes it more stable. So what happens when you get too excited about writing stuff? When we have less electrons around it, okay, that's the same as missing electrons, that's going to be less stable. Okay? So what does that mean back to our system over here? Okay? Well, this structure versus this structure. Okay? The zero, or the top one, has less electrons around it. It's going to be less stable. Well, the next one down has more electrons around it, so it's more stable. Okay? The next one down, if we continue that out, we'll have 10, we'll have 15, which would suggest this bottom one is the most stable, and the top one is our least stable. And I don't know about you, but we're saying top and bottom and all of that, and that's difficult to kind of put a frame of reference on which one we're talking about. So it might be nice if we had a labeling system. And it turns out we do. We can count the number of carbons connected to our central atom. So in that bottom case, there's 3 carbons connected, and we can call that, whoops, man, I am just not on fire for this video, tertiary. The next one has 2 carbons. Well, 2 carbons we could reference as secondary. The next one up has 1 carbon. We refer to it as primary. And then the top one gets an entirely different naming system, which I disagree with, and I would argue it has 0 carbons connected to it, so we should call it zeroary. Nobody calls it zeroary except me. It is typically referenced as a methyl. Okay? If you want to start using zeroary, I highly encourage you do, because I think it just sounds hilarious, and I think it's more appropriate. Okay? So our conclusion of this, cation stability, a zeroary is the least stable cation, and tertiary is the most, which means if I start with a molecule and I explode it, it's going to explode in a way where I'm going to get more tertiary pieces than I will get zeroary pieces. That does not mean it creates tertiary. That just means if they are there, I would expect them to exist in a higher concentration than I would of the zeroary. Okay? So here's the labeling system that I had intended to pop up and forgot. So we can reference those. Our cations and our radicals act very similarly, so that's nice to have in hand. And then what we'll do is throw in an extra little test question on you here. Okay? If you're understanding the stability here, you should now be able to go through and tell me the stability of the anions. Okay? So there was a question that popped up. I don't know if you got it right or not, so let's real quickly walk through it. What makes each of the anions reactive? Okay? Well, they're all negatively charged. They're all unstable because they have an excess of electrons. So if we have too many electrons, that's also bad. Okay? So excess electrons means more electrons is unstable. Less electrons is going to be more stable. Okay, and for those of you saying you screwed this up last time, touche, I appreciate that. Okay, always rain pain down on somebody who screws things up for you. So this is correct. If we have more electrons around our anion, it is going to be more unstable because the problem that made it unstable was that excess electrons. Okay? So with that information, you should now be able to go through, if you didn't correctly do it last time, and answer this question more appropriately. Hopefully you saw that our tertiary anion is actually now the least stable. Man, is now the least stable because it has more electrons around it. Those carbons are contributing more electrons in. That's putting more negative charge in the exact same spot that one becomes bad. So we get a swap in the stability, right? Oftentimes people will just go through and memorize this. That's fine, but I would argue if you understand what makes things stable and unstable and then adjust your expectations behind it, you now have a way to apply that to other situations. Okay? So, mass spec. Really what I want you to get out of this, we exploded a bunch of stuff, we get pieces. Okay? There are 5 big things that I want you to really kind of nail down. 5, and we'll sort of call it 6, and we'll look at the 6th here in a second, that you should really nail down right away. These first 5 are the big ones. You should be able to tell me the molecular weight of your compound. Okay? The directions here say peak furthest to the right. It's the tallest peak furthest to the right. Not the tallest peak, but the tallest peak furthest to the right. Okay? There are some weird exceptions on that, but for the most part, that holds true. So if you find your peak furthest to the right, find the tallest peak, usually within 3 units of that, that's your molecular weight. That's a useful bit of information. After that, all our other analyses are based off of that signal. So you have to know where that signal is. If we look at that value and it is an odd number, then I know there are an odd number of nitrogens present. I have some information about the atoms present. That's kind of cool. If it's an even number, that doesn't tell me there are no nitrogens. It just tells me there's either no nitrogens or an even number of nitrogens. Okay? So it's not a perfect system, but it gives you some information. The M+2, so remember that peak that we found furthest to the right, that tallest one, now we want to look at 2 units greater than that. Okay? If there's another signal that are 2 units greater than that, now I know I have bromine. Okay, well, why? Remember, mass spec measures mass. Well, what's special about bromine? Well, bromine has 2 common isotopes. One, 79, one, 81. Note a difference of 79 to 81, 2. Exactly. That's the +2. Okay? What's special about those 2 isotopes is they show up in roughly half of your samples. So if I look at bromine, half of it is isotope 79, the other half is isotope 81. So when I go through and look at a random collection of pieces, I would expect to see an equal percentage of bromine, 79 and bromine 81 in that sample. That's why we're seeing those 2 peaks next to each other. Same kind of thing, it's an isotope effect for chlorine, M+2, your rate or your ratio is 3 to 1. Okay, so your M+ is 3 times, your +2 is a third that height, and that's what's being represented here. Why? There's 2 common isotopes for chlorine, chlorine 35 and chlorine 37. Again, there's your +2. The 37 shows up 25% of the time, and the 35 shows up 75% of the time. There's your 3 to 1 ratio. Okay? A peak at 127 generally means iodine is present. I should really just delete this one from the overall slides. Iodine just doesn't show up very often, and it is so massive that if you're seeing iodine in your sample, you'll see just a massive molecular weight. Your M+ peak will be big because it has to have iodine and now all those carbons and whatever pieces go along with it, which means your mass spec shoots up as far as mass very, very, very high. So if you're seeing a large weight, that does suggest iodine is present. Okay? And that's kind of it. Like, those are the big things that you should get right away. So what does that mean when we go through and look at a spectrum? Okay, so here's a mass spec. Okay, you'll notice that we're seeing that M to Z, that mass to charge ratio. The abundance, our vertical axis, is normalized to 100. Okay, so the instrument just counts however many things, and then it just says whichever one was the most, that's now 100. Everything is scaled according to that. Okay, so it's a normalization. So I would go through and look at this. We've got a lot of stuff already labeled out on this, but let's walk through our directions. The first thing we said we wanted to look for was the M+. Okay? We said the M plus was the peak furthest to the right, and if we go furthest to the right, there's our peak furthest to the right. We now look for the tallest peak within 3 units of that, and that's that peak. It's that one. Okay? That one was conveniently labeled for us, which it typically is because it can be hard to read all the dashes on the bottom, and that's 86. That means that is our molecular weight for this particular compound. Okay? It has a molecular weight of 86, and we'll break that down in a second. The next thing we said to do was look for a +2. So an M plus 2 would be an 88. Do you see an 88 in there? Well, no. What does that mean? That means there is no bromine. There is no chlorine. That's the point of that. The other thing, which I forgot, is your M plus odd. Is 86 an odd number? No. So what does that mean? No nitrogen. The structure was already given for us, and note, no bromine, no chlorine, no nitrogen. The last bit of information that I asked you to analyze would be looking for that signal at 127, okay, or really, really large mass. The mass is under that value. There's no way iodine can be present. We're less than 127, which means no iodine, okay? That's good. Those conclusions should be made very, very, very fast, okay? The last one that's a little bit more challenging, and actually even before we look at that, you might then say, well, what about all of this other stuff? Is there useful information there? Yes, the textbook does address that useful information. It is up to you if you want to look at it. You can use that information. It is not going to be commonly tested on, so use your best judgment on deciding that. The last thing that I would ask you to go through and do, this video is taking way longer than I wanted, was take a look at that 86. Since I don't have any evidence of all the other ones, I'm going to say that it is composed of carbon and hydrogen. Carbon has a mass of 12. How many times does 12 fit into 86? I think it's 7, and we would get 84. That would mean 2, and I would have a signal or a formula of C7H2. Okay? Well, that's not a lot of hydrogens. So what if I had C6H, and since I removed 12 on our carbons, that has to be accounted for somewhere. I'll add that to our hydrogens, H14. Okay? Both of these are potentially valid formulas. 1, 2, 3, 4, 5, 6 carbons. Interesting. 3, 6, 9, plus 1, 10, plus 2, plus 2, 14. The formula matches. Sweet. Okay? That's the kind of utility of looking at the pieces behind it or that data, because it can get you information that could lead you to a structure. It's not a perfect structure match unless you dig into the fragmentation pattern. Okay? How do you do the fragmentation patterns? The same way that we did the molecular weight peak, we would go through and say, well, 43, how do I get a 43? Well, that 43, 12 into 43, 3, whoops, not 60, 36, 4 and 3, 7. We're looking at 3 carbons and 7 hydrogens, assuming I did that math correctly. What kind of pieces could have 3 carbons and 7 hydrogens? Okay. Give you a big old hint. 3 carbons and 7 hydrogens. Why would I expect to see a lot of this piece? Well, that's a secondary carbocation. That's the most stable carbocation I could form. There it is. Okay. That's how we're getting these pieces and how they're coming about. Okay. So the fragmentation pattern can help you kind of predict these things. With that, we're actually done with mass spec way longer than I wanted to be, and I'm late to office hours. So I hope that works. Let me know if you've got questions behind it. Again, focus on the easy stuff. If you want to dig into fragmentation, you can, but you are not expected to. Have a good day.